I would like to work through this vector surface integral with you two different ways. So the first thing we're going to do is compute this flux just directly as it's given to us, meaning that I'm going to do a vector surface integral. And then if you haven't seen divergence theorem, that might be all that you want to see, but I would like to come back and re-answer this question from scratch using the divergence theorem because it's actually a lot easier that way. So we'll start by just doing the vector surface integral. What is the first step? The first thing we need is a parametrization. All right, so how are we going to parametrize this? I am going to use spherical coordinates because we are working on an upper hemisphere of radius 3. You could use rectangular coordinates, you could use polar coordinates, but the advantage of spherical coordinates is that it's going to avoid any kind of square root in the z component. So let's write r of u and v. This is going to be my parametric description of the surface. Notice the radius of the sphere is always 3. So if I said that and you thought, wait, spherical parametrization requires 3 coordinates, and here we only have 2 coordinates. The radius is fixed at 3. In fact, I'm going to write it out front. And then our coordinate by coordinate description for this sphere will be cosine of u, so that's like theta, the angle rotation in the xy plane, sine of v, sine of u, sine of v, and then cosine of v, where I'll make a note here that theta goes all the way around. So u is between 0 and 2 pi. But since we only have the upper hemisphere, the angle v is going to go from 0 on the x-axis to pi over 2 to land us on the xy plane. All right, so those are the bounds on our parameters, and that will go into the bounds on our integration. Sorry about that messy 0. What we need to do now is compute those vectors of partial derivatives. So I'm going to do r sub u. Leaving the 3 out front, that's going to be negative sine of u. Oops, careful with your u's and v's. So negative sine of u, sine of v. Cosine of u, sine of v. Hesitated for a moment there because, again, lots of trig and u's and v's. So cosine of u, sine of v, and then 0 because the z coordinate has no dependence on u. I want to do something here because ultimately I'm going to take a cross product, and if I can pull as much in front of the cross product as possible, that simplifies my computation. So noticing that we have sine v here, and 0, which you could think of as 0 sine v, let me pull the sine v out front and write this as 3 sine of v times just negative sine of u, cosine of u, 0. Let's do the same thing now, but with the v partial derivatives. Okay, going back to here, we'll have a 3 out front. Let me see if I can squeeze that in there. That's a 3. Cosine of u, cosine of v. Sine of u, cosine of v. And then negative sine of v. All right, let's cross these. I'm going to call this vector n. And we're going to take the cross product. I'm going to do some simplification. I'm actually going to phrase it in a way that you might not initially like. And keep in mind also that at the end, when we're done computing n, we need to assess whether or not the cross product is oriented correctly. We're told that our surface is oriented with outward pointing normals. That's the direction we would like n to take. Okay, just put that on the back burner now, though. So let's go ahead and do this cross product. Leaving terms out front is going to be 9 sine of v. And then for the first term in the cross product, it's going to be, let's see, this times this minus 0 times that. So that's negative cosine of u sine of v. And then the second component is going to be 0 times that times, minus negative sine u, negative sine v. So overall, that's negative sine of u, sine of v. The third component, let me write down the answer. It's just negative cosine of v. For that third component, I'll write it out down here and then we'll erase it in a moment. But the third component of the cross product came from this times this. So that's negative sine squared of u cosine of v minus this times this, but that's going to be minus cosine squared u cosine v, which you can factor out the negative cosine v, leaving you with the sine of u squared plus the cosine of u squared. And then from the Pythagorean identity, hopefully you recognize that that is 1, so that overall this is negative cosine of v. Okay, I'm going to pause here, and what I would like for you to do is answer one question. Is this vector correctly oriented relative to the description of the surface that we were given? The answer is no. If you look at cosine of v for v values between 0 and pi over 2, cosine of these angles is positive, or greater than or equal to 0. By negating it, that makes the third component of this vector field negative, which means the z direction would point down. So these vectors, sorry, dropped my marker, these vectors are pointing down kind of into the sphere. That's fine. That just means that when we set up our computation, we need to drop a negative sign in front because we are looking at the reverse orientation here. So all you need to do is just pick up a negative in front of your eventual computation. Okay, that's the first observation I wanted to make. The second one is a little bit more subtle if you haven't seen this. And that is, notice how similar these coordinates are to the original parametrization. In fact, let me do something. I'm going to like undo some of this factoring out front that I started with. I'm going to take this 9 and I'm going to drop a 3 into each of these coordinates. So 3, 3, 3. Okay, so it's a leading 3 out front, and then I've brought 3 into each of the coordinates. And just to make this extra messy, let me also pull out this negative like that. All right, so now out front, I have negative 3 sine of v times the xyz coordinates, 3 cosine u sine v, 3 sine u sine v, 3 cosine v. The reason why I've done this is it's not necessary. I'm actually just trying to illustrate the geometry of the sphere for you. It's nice when you're working through a computation to make sure that things make sense to you visually. So I could take this in now. In fact, I should probably do this because this is extra messy, and write this as negative 3 times sine of v times x, y, z, because this is x, y, and z with a 3 distributed. So x, y, z. Yes, I am mixing rectangular and spherical coordinates together, but you could also think of this as x of u and v, y of u and v, z of u and v. So it's almost like a shorthand. Okay, I wanted to bring this up because if you think about a sphere and you imagine what vectors orthogonal to the sphere would look like, they're going to radiate outwards. And the fact that I just used the word radius or radiate is what I'm trying to bring up here. XYZ is the position vector for any point on the sphere. So if you imagine a point on the sphere and the origin and the vector going from the origin out to the point of the sphere, that would have coordinates x, y, z. So we're saying a vector field orthogonal to the sphere is a multiple of that vector, and that's exactly right, because if you have a sphere and vectors which are perpendicular, they have to be some multiple of that position vector because we've got orthogonality set up between the position vectors and the sphere itself. It's kind of like spokes on a wheel. It's a little bit easier to sketch in 2 dimensions. Okay, so I wanted to bring that up. Now we are ready to start putting together the double integral that we're going to set up and evaluate ultimately in order to compute this flux. I think what I would like to do is actually stick with these coordinates for a moment. So let me do one more computation before I erase most of this and we start with a fresh board. And that is, let me keep mixing together rectangular and spherical coordinates for a moment. What would f dot in look like? Well, our vector field f is yxz dot this leading factor, negative 3 sine of v, xyz. Okay, so this doesn't seem too exciting at the moment, but I'm going to write negative 3 sine of v times xy plus xy is 2xy, then plus z squared. Okay, so in a moment, I'm going to pick up with this. This is going to be the integrand that we are going to start evaluating. You can make sure you're setting it up correctly. So take a moment to go ahead and take the flux integral expression and convert it into a double integral that we can then evaluate with respect to u and v. If you don't like that I'm doing this, by the way, you don't have to. So you could leave it in this form. You could go ahead and put in these descriptions for y, x, and z if you'd like. So the fact that I'm mixing coordinates together is just something that I'm choosing to do in this problem. It's not obligatory. All right, let's set up and evaluate this flux integral. So across our upper hemisphere, we would like to do f dot ds. Okay, that's saying literally we want to do a flux integral. How do we evaluate that? I'm going to bring in my negative here. This is from that orientation issue that we discovered when we did our cross product of r sub u and r sub v. Now I'm going to integrate with respect to these bounds. I don't think there's any reason here to order them a certain way. So we'll go from 0 to 2 pi and from 0 to pi over 2. F dot in du dv. So that was the computation I left you with over here. So that's going to be, what was it, -3 sine of v. And then bringing back in the x, y, and z coordinates, we had written it as 2xy plus z squared. Where again, x, y, and z here are placeholders for this parametrization. And then we will do dv, du. Okay. All right, we've got negative, negative, so we'll think of that as just positive. And then here, can keep going. So 0 to 2 pi, 0 to pi over 2. I probably should have pulled that 3 out front, but I'll just leave it. 3 sine of v. And then let me now convert these back. So again, you didn't have to go into this notation if you didn't want to. We have 2 times, 3 times 3, because we have 3 cosine u sine v, 3 sine u sine v for x and y. And then we have cosine u sine v sine v. So cosine u sine of v squared. Hopefully you're anticipating that something's going to happen here with this product of cosine and sine terms, and so we will go through that in a moment, but let me finish with plus z squared is 3 squared cosine squared, so 9 cosine of v, that quantity squared. All right, notice here that cosine u sine u, this product is going to enclose as much positive and negative area as we travel from u equals 0 to u equals 2 pi. And if you don't see that right away, or you need a little bit more persuasion, 2 cosine u sine u is the same thing as sine of 2u. Like that. So here I've put these together. Sine 2u has period pi, which means that as u goes from 0 to 2 pi, we have 2 full sine waves. So that goes up, down, which means that the total amount of area enclosed under the graph of this function, or between the graph of this function and the u-axis, would be 0, cancels out. Okay, so all that to say that this whole expression here is going to produce a double integral of 0 because of this u action. So we just drop it. So that's good news. And you actually could have reasoned that out by looking back here at the product of x and y. If you thought about the product of x, y as you go around the upper hemisphere, it's symmetric. So you've got x, y is positive in the first and third octants, negative in the second and fourth octants, and it's all going to cancel out. So you could have actually used this symmetry also to figure out that this whole part of the integral is going to vanish. Okay, that leaves us with the 3 sine v, the 9, the cosine squared v. Everything left in the integrand only has v dependence. So as I write this, I'm going to actually take this double integral and write it as a product of 2 independent single integrals. You don't have to do that, so that's my choice. 3 times 9 is 27. And then for the u part, we have 0 to 2 pi, 1 du. And then 0 to pi over 2, sine v cosine squared, the cosine of v squared dv. Again, this product here, optional. We're going to do u sub here to finish this. U is going to be cosine squared. Sorry, misspoke. U is going to be cosine of v. Du is going to be negative sine of v, and we will also need to change our bounds. Okay, so what do we have so far? We have 27 out front. Integral from 0 to 2 pi of 1 is going to be top bound minus lower bound. And then here we have u squared times negative du. All right, so overall this is going to be negative u squared du. Changing the bounds here for this definite integral that we're evaluating with u substitution. When v is 0, u is cosine of 0, which is 1. Whereas when v is pi over 2, u is cosine of pi over 2, which is 0. Hope that these are clear which is which. Okay, we're basically there. Let's see, 27 times 2 is 54 pi times, you can use this negative to flip the bounds if you want. It's not really necessary. So we've got negative u cubed over 3, 1 and 0. Plug in 0, it vanishes, minus negative 1 cubed. Did I say that right? Yes, minus negative 1 cubed over 3 is times a third for this. Sorry, I'm misspeaking a little bit. I'm just trying to say this is 1/3. Okay, so 54 pi divided by 3 is 18 pi. Okay, so evaluating this flux integral using a fairly traditional approach, meaning parametrize the surface, compute those partial derivative vectors r sub u and r sub v, cross them, evaluate the orientation, and then do f evaluated on the orientation dot that orthogonal vector, checking the orientation as you do so, and then setting up ultimately just a double integral, resulted in 18 pi. If you have not seen the divergence theorem and you just wanted to see a flux computation, we're done. But what I would like to do is come back in a moment and redo this computation using the divergence theorem. It's going to be much faster. It's also just a really nice computation, so that if you would like to see this done a second way using divergence theorem, we will do that too. All right, the divergence theorem would be my personal preference for how to solve this flux integral, but there's a little bit of a catch. So even though I think the arithmetic is ultimately easier, you have to be sure that you're proceeding carefully when you translate from this flux integral across a hemisphere to the divergence theorem setup, because it's important that you remember the divergence theorem requires you to be working with, I'm not done with this picture, it looks terrible, a solid region which is fully enclosed by, say, surface boundaries. So we had the hemisphere of radius 3. And what I want to do is connect this to the solid region which is inside the hemisphere. But do not forget that at the moment there's a gaping hole down here at the bottom. So anytime you're doing this kind of transition from, say, a surface integral to a solid three-dimensional computation using the divergence theorem, you have to check that your region that you're ultimately going to move into is fully enclosed by surfaces which you can describe. So this solid blob inside the hemisphere is enclosed on top by the hemisphere, but we need to add to this a lid. Okay, so on the one hand we have S, and then I'm going to call this L for lid. This lid is the disk of radius 3 in the xy plane. So it's a solid disk in the plane z equals 0. What the divergence theorem tells us is that if this interior region, so the solid three-dimensional blob that I'm enclosing with S and L, is called E, then the triple integral over E of the divergence of our vector field, dv, that's the volume element. So here, this is just a triple integral. It's not a surface integral or anything like that. This is going to be a scalar. This could look something like dx dy dz, depending on how you set it up. This is equal to the double integral over what I'll write for now as the boundary of E, so that's boundary of E, of just f dot ds. So that is the content of the divergence theorem. Okay, this boundary, though, has two pieces. So the right-hand side turns into the double integral over S, the upper hemisphere, of f dot ds. This is what we actually want to find, plus the double integral over L, which we've just brought into the problem, f dot ds. Okay, so this is what we want. That means that we can find what we want if we can do this triple integral minus this flux integral, where hopefully both of these are easier than this one directly. So let's start with this lid. And this one happens very quickly because if we think about our vector field, where again, we want to imagine, should add this to my picture, that the surface, or this region rather, is oriented with outward pointing normals. That's what we already had for the upper hemisphere. But we also need to kind of connect it down to the lid. If you imagine outward pointing coming down to this lid down here, that means pointing straight down, parallel to the z-axis. Okay. So there's a little bit of magic that happens in this problem. If we do f dot in, where I imagine that this is like this downward pointing lid, without even parametrizing, I can tell you what the answer is going to be. And it's just because this problem is kind of set up to be nice. So f was y comma x comma z, but on the lid z is 0. We're working in the xy plane. So this is for that reason. And then dot, well, we want to dot it with vectors which are pointing straight down. So it's 0, 0, something. You know, if we take some sort of unit normal, it'd be 0, 0, -1. But if we were deriving this from a parametrization, this might change. But the point is it would have this form. Now, if you look at the dot product, you get 0, 0, 0. So this extra piece that we're adding in is 0. And I'm kind of laughing because that means that if you tried to set up this problem with the divergence theorem and you forgot about the lid, you would actually get the right answer, but it would be wrong. So you should remember the lid. But in this particular problem, it turns out that it contributes nothing to this computation. So this is kind of happy coincidence in case you forgot that. Now we can just find this triple integral in order to find the flux computation that we want to do. We know the answer is 18 pi, so let's see if we can get it again. What I'm going to do is step aside so that you can finish writing this down and go ahead and compute the divergence of f. All right, the divergence of f is 1. So what you should have found is that when you compute the divergence of this vector field, y, x, z, you want to do d dx of y, that's 0, plus d dy of x, that's also 0, plus d dz of z, which is 1. Okay, so that turns into this integrand. Remember, this integral, it looks fancier than it is at first glance because you have this operator in there. But what we're saying is now we just want to integrate 1 across this solid region. So it's just a triple integral. And what it's actually asking us to do in this particular problem is just to compute the volume of E because the integrand is 1. So let's see if we can squeeze it down here. The triple integral of across E of 1 dV, because this is 1, this is equivalent to the volume of E. If it had been 2, it would be twice the volume of E. It could have been something more interesting. It could have been x plus y or something like that, and then you'd be looking at doing a more classic kind of anti-differentiation action. But we have something that works out very nice. So we just want the volume of E. That is a geometric computation we can do because we're looking at half a sphere of radius 3. So half a sphere of radius 3 is 1/2 times 4/3 pi times the radius cubed. Okay, hopefully we're going to get 18 pi. So this is 2 over 1, meaning, let's see what I'm going to do. 2, knock that down, cancel that out. So 2 over 1 pi times 3 squared, giving us 18 pi. All right, I hope you enjoyed this second approach to solving the problem using the divergence theorem. computationally, you can see it's much cleaner than the flux integral that we started with. Part of that is because this problem was written for the divergence theorem. So that so much magic happened was by design. However, I think it's a great way to rethink this problem. What I really want you to take out of this demonstration is how to make sure that the solid region that you're evaluating when you pass from a flux integral to a triple integral with the divergence theorem, make sure your solid is fully enclosed. So that's really the most important aspect of the computation that we just did, was the addition of this lid piece. Okay, thank you for your attention.